Work one evening and I was getting undressed, and I don't know how, but my hand slipped across my breast and I felt this huge lump, and I had never felt it before. And my son heard me because I started to cry because it was such a, a traumatizing sort of thing.
That traumatic day 3 years ago was the start of Teresa Murphy's fight against breast cancer. Her disease was aggressively treated with a mastectomy and chemotherapy, and today she is well. But for many older women, the same is not true. There is now evidence that older women are less likely to receive the appropriate treatment for their disease than are younger women.
I'll just come in a little bit more. That's good.
Researchers at Brown University conducted a study of how women in different age categories were treated.
Okay, now this is the medical record abstract form.
Yes.
We ended up with 494 women with breast cancer identified in the hospitals in Rhode Island. We broke those women into 3 age groups, ages 45 to 64, 65 to 74, and 75 to 90.
Only women healthy enough to receive the full treatment were included in the study's chi-square analysis. For women in all the age groups, the accepted treatment for breast cancer that has spread is a mastectomy, surgery to remove the breast, and follow-up chemotherapy. Of women in the 75 to 90 age group, only 1/3 received chemotherapy after surgery, compared to 2/3 of the younger women. This difference was statistically significant at the .003 level, a disturbing trend.
Older women are not being given the same alternatives in terms of treatment. I think that the bias in the term on the part of the physician is that A, he or she is not sure the patient can tolerate the therapy. And I think that's an age bias. And B, I think whether it's conscious or subconscious, there's this idea, well, she's already 75, So I'm not going to treat her like a 45-year-old woman where I'm really shooting for a cure because she doesn't have that long to live.
In fact, women 75 years old will live on average 12 years. Without chemotherapy, cancer is likely to recur within 5 years. So a physician's age bias may be affecting the quality and the length of life for the elderly woman. How to draw up discrete age categories from the continuous group of all women's ages is a difficult choice. The researchers decided on 3 age groups. But how would narrowing the categories affect the results?
While we find with 3-category age variable, we end up with a p-value, a probability value from the chi-square distribution that is something on the order of .003. By the time we're up to a 5 or 6 or 7 category age variable, we're at a probability value of just .03.
How about where the actual scar was? Does that?
While even a p-value of .03 is often viewed as significant, it reveals the impact that choice of categories can have. The conclusion drawn here is that health professionals are discriminating by age, a bias physicians need to be educated about.
They may not be aware even that they're really not doing the whole 9 yards on the older patient. So their bias bothers me, but I think that's a correctable item now that it's been identified.
The importance of doing the whole 9 yards is clear from success stories such as Teresa Murphy's. Getting the definitive treatment enabled Teresa to go on with her life, giving to her the chance to make her older years as full of life as any other years.
Oh, well, that's no good.
I just want to work for 3 more years, and then I'd like to be able to retire and just go and visit my friends and just have a good time. Just enjoy the rest of my life.
Another comparison in the breast cancer study was between age and the appropriateness of diagnostic tests. In other words, whether women were given a mammogram and breast lump biopsy. Both these classifications, age and diagnostic tests, are categorical. We want to know if there's an association between them. This is a relationship within a single population, which is different from comparing 2 populations as we did with teeth. Fortunately, we can use a 2-way table and the chi-square statistic in both cases. We'll use data from the breast cancer study to see how to calculate a p-value for chi-square. Here's a 3x2 table for the number of women in each age category who did or did not receive the appropriate test. As before, we'll express the counts as percentages of the row totals to get a preliminary comparison. In this case, we can see that older women were indeed less likely to receive the appropriate test than younger women. Now we'll use the counts to compute a chi-square statistic to determine if the relationship is statistically significant. Here are the row, column, and table totals. As before, we calculate the expected value for each cell by multiplying the row total by the column total and dividing by the table total. With the values for observed and expected counts in hand, we find a value of 7.35 for our chi-square statistic. Now we need to convert that number into a p-value. We do that by comparing the value of the test statistic with critical values for its distribution. We did exactly the same type of thing in finding p-values for our z and t statistics. Here's the distribution of the chi-square statistic when the null hypothesis is true. Obviously, the chi-square statistic marches to a different drummer than the z and t statistics. It's not at all symmetric. It's plainly skewed to the right. This distribution shows us the behavior of the chi-square statistic in a very large number of samples. If you think of the curve as a probability distribution, it begins to make more sense. The curve starts at 0. As we saw, a chi-square of 0 means there's a perfect fit between the real data and the model predicted by the null hypothesis. You can see from the curve that the probability of getting chi-square values near 0 is high, and then drops off steadily as the values increase. Also, just like the t-distributions, chi-square is really a family of distributions, one for each degree of freedom. As degrees of freedom increase, the distribution becomes less skewed. Finding the degrees of freedom for the chi-square statistic is easy. If our two-way table has r rows and c columns, the degrees of freedom for the statistic are r-1 times c-1. So for a 3x2 table like we have in the breast cancer diagnosis study, the proper degrees of freedom are 3-1 times 2-1, which equals 2. To see how significant a particular chi-square statistic is, simply compare its value to a table of critical values with correct degrees of freedom. So we look in the row for 2 degrees of freedom and find that 7.35 is very close to the value for 0.025. The p-value is very close to 2.5%. This p-value is small enough to confirm that there is indeed a significant difference in the use of appropriate diagnostic tests for breast cancer among different age groups. When using the chi-square test, remember that with large samples, even a very small association will appear statistically significant. The general rule is use a comparison of percentages to get a sense for the size and strength of an association. Use chi-square calculated from counts to find out whether an association that large is likely to occur by chance alone.